This is a continuation of a video walkthrough for the Math 143 Semester 2 CWI practice packet. We're on question number 17. It says find the dimensions of the rectangular garden whose perimeter is 26 feet and whose area is 30 feet square or square feet. Let me draw this. I want to get a visualization. They say it was some kind of rectangular garden. Now, maybe I'm not drawing the rectangle in the correct direction, but whatever. It says the perimeter is 26 feet and the area is 30 feet square. So the area is the amount of space sort of inside, right? And the perimeter is going around. The problem is there's lots of ways to get an area of 30 by doing base times height. Like this could be 10 times 3 or 15 times 2 or I don't know, all kinds of options, right? Same thing with the perimeter of 26 feet. I mean, maybe it's a couple feet on over here and then 10 feet over here and 3 feet over here. That could make the 26. Let's write an equation for this. So we can call this like a length and maybe a width. They use the terms length and width. And of course, we know that area is the whole length times width. So we have that 30 feet square is our length times width. But like we said, there's lots of possibilities of lengths and widths that fit that equation. But we have another equation, that's perimeter. The perimeter is all of these added up. Now don't forget there's another length here and another width here. You could say it's length plus width plus length plus width. In other words, some people write it as 2 lengths plus 2 widths all added up. Now of course we have here that perimeter is actually 26. So we could say 2 lengths plus 2 widths has to make 26. Now we can try and guess and check to try and see what possibilities we could have for lengths and widths. In fact, I think I mentioned one briefly as a possibility when I was thinking all the options for doing this. Like really we could have a width, width I believe is the shorter one, yep. So they mentioned it here that width will be the shorter one. So the width could be 3 and the length could be 10 and that would be an area of 30. That's for area. Of course, we could have another possibility. I think I mentioned 2 and 15. 2 times 15 would be 30. But even just stopping there, if I just check that as for one of my lengths and widths for perimeter, I actually have already found the answer. The perimeter, if I did 2 times the length, if I did 2 times the 3, that would be 3 over here and 3 over there. That would make 6. And if I did 2 times that length, that was the longer one, of 10, 10 here and 10 there, that would be 20, and then I see that makes the 26 perimeter that I want. So I've got an area of 30 and a perimeter of 26. So it looked like this works. And of course, that was with a length of 3. In fact, let me label that on my picture so I could visualize that, checking my area. And a width, you know what? I'm sorry, I have that switched. Width, let me scroll over so we can see that. They say width is the shorter one, and I labeled it there. So here, the width was 3, and the length was 10. So if I put 10 here and 10 there, you would see that those produce the area of 30, and they produce, if you add them all up, the perimeter of 26. Now, how could you do this without knowing that, without sort of just seeing it? You could use a technique we used a minute ago with doing the circles and the lines and finding out where they intersect. I have actually 2 equations here. I have a perimeter equation and an area equation. Maybe I should have highlighted them in different colors like I did for the other problems. So if I can switch it. So what I can do is I can actually just graph these things using technology. And so let me type in the perimeter one since I can see it. 26 equals, I could go 2L and 2W, or I can go like 2X plus 2Y if I like to use the normal X and Y. So length is X and Y is the W. And then of course here it's just 30 equals, the X times the Y. And so now I see I actually have 2 different math situations. And check it out, nothing intersects over here, but those 2 things intersect each other here at 3 and 10, And here at 10 and 3, oh, wait, two possibilities? It looks like it's just 10 and 3 and 3 and 10. So one of them is 3 and one of them is 10. They told us that the shorter one will be the width. So 3 was the width and 10 was the length. Instead of guessing and checking for this other example, let's use that calculator technique of graphing. So let's set up our equations. Again, we got a rectangular table. All right, excellent. Looks like, again, width is the shorter one, so those will be the width. This will be the length. And it looks like now it says the perimeter is 16. And, of course, perimeter for a rectangle is 2 times length plus 2 times width. So if the perimeter is 16, then some kind of 2 times length and 2 times width needs to make that 16. That would be my first equation. I'll colorize this one. Now we also have the idea of an area. Of course, don't forget, area is length times width. And so our area is 12. And so some mystery length and width have to make an area of 12. So I can make those equations, and then I can solve that system of equations just by graphing it. So let's punch in this first one. 16 equals 2x plus 2y. And then let's go over here and let's do this other one. There we go. It was what? 12 equals x times y. And again, we get a similar picture here, but the key is, where do those two things meet? It looks like they cross at 2, 6 or 6, 2. So it looks like one of our answers is 2 and one of our answers is 6. Remember that the width is going to be the smaller one, so that'll be 2, and the length will be 6. And of course, if you multiply those, 2 times 6 is 12 feet square for the area in the middle. And of course, if you add 6 plus 2 plus 6 plus 2, well, 6 plus 6 is 12. 2 more and 2 more makes the 16 total. So there we go. What length was 6 and the width was 2. Moving on. Here we go. This is a quick one. The equation of a conic section is given its familiar form. Identify the type of graph the equation has without actually graphing it. Of course, we could actually graph it to double check our work as we practice here, but we should know this one. This one's got a plus between there. This is a good old ellipse. If it had a minus in there, it would be a hyperbola. Of course, if it had a plus and these two numbers were the same on the bottom, it would be a circle. Or even if it was a circle, like for example, if I just make up another problem similar to this, if they were both 16 on the bottom, that would be a circle, but we would actually not write it in that way. We would multiply everything by 16 so that it clears those fractions out, like we've done in the past, and this is the form for a circle. But this problem is not a circle, so it is an ellipse because it is uneven on those two numbers. Let's look at the next problem. The next problem has that subtraction between it. That is the hyperbola. That should be a quick one. All right, down here it says use synthetic division and the remainder theorem to find the zeros of the following function. Okay, we did synthetic division, and we've talked about having a remainder of some sort, but really all we care about is finding the zeros. Now, we had a technique for finding the zeros, at least to even get started here. What could be the zeros? We could look at combinations of P over Q and all the possibilities that we could have for a zero. What I'm going to say is, let's use a calculator to go even quicker. Remember, our calculator can actually help us see the zeros because x-intercepts are the zeros. So let's graph this thing and see what kind of information we can find from it. Some people might say, oh, that's cheating. No, it's actually using our tools, our technology. When people build a house, they don't use just rocks and sticks to build it. They use lots of amazing technology to help us build an amazing house. So let's use our technology to get an amazing answer. Let me zoom in here a little bit. And I think I see some of our zeros. In fact, how many zeros do we expect to find? Since this is a third degree, we should see 3 zeros. And actually, I think I see 3 zeros. I see one here, -1/2. I see one here at +1/2. And I see one here at 3. So I just found all the zeros really quickly. Whoops. So we have, what were they? X was equal to -1/2. I like to write it as a fraction, not in decimal form like the calculator did. We had +1/2, and I believe the other one was 3. Of course, we could plug them in there, and we can check and see if it does indeed produce a 0. Let me double check it. Yep, 3/2 and -1/2. Excellent. Let's move to the next one. This one says use synthetic division and the remainder theorem to find the zeros. Again, like we did before, let's see if we can use a calculator to get us started to find some zeros. In the last problem, it actually helped us find all the zeros. Let's see, let's go x to the 4th minus 13x. To get the exponent, use that shift number 6, and that uses that caret or that arrow pointing up. You could also go down here into the keyboard and use the exponent button to get into an exponent. But here we go. Let's lower that keyboard for more space. How many zeros do I expect to find? I expect to find 4 of them. I'm hoping I need at least 4. Looks like I can actually see all of them. None of them are invisible or imaginary. So we got 3, 2, and -2, and -3. So there we go. We had x was 3, and x was 2, and x was -3, and x was -2. We found all 4 of them. Let's go to the next one. Number 23 says, write your equation in interval notation. Oh, we got to solve this thing and then write our answer in interval notation. Use integers or fractions for any numbers in the expression. Write an answer as an exact answer. Use radicals if needed. Well, what do we got here? Here we have an inequality again, like earlier in this practice packet. And they say to write the answer in interval notation. Just like before, I like to always think of this thing first as just being good old equals. Well, what would make a fraction equal 0? If you remember, a fraction can equal 0 when the numerator is equal to 0. So what's going to make that equal to 0? I can solve it by dividing both sides by 2. And then I get x equals 0. So that is good. That will make it equal 0. This is what we call a 0. I almost circled it as my answer, but remember, we don't want to know when it equals 0. We want to know when it's less than 0. Now that was a 0 on top. That was okay. What about zeros on bottom? On bottom is bad. That's an asymptote. That would be a bad asymptote. And so we want to know when the bottom is 0, because that would be bad for this whole problem. And so let's set it equal to 0. Of course, I could subtract 3 to both sides. And I see that that's when x is -3. That's an asymptote. Oops, I spelled that wrong. Oops, I'm crossing it out. It should be asymptote. There we go. Now, how do we solve this thing for when it is less than 0? Well, we found when the 0 was on top, and that's okay, and we found a 0 on bottom, and that's bad. To find when it's less than 0, we make a sign line. This is like we've done before in an earlier problem with inequalities. The deal here, though, is we need to mark the 0, and we need to mark the asymptote. That's at -3. So remember, I like to even label this since we have 2 different types of equations. I did it again where I spelled it different than I usually do. We have 2 different types of situations here, I should say. We got the asymptote and we got the actual 0. Now, we want to know on the left side and the middle side and the right side what's good, what's bad, what is what we want. Let's see. I could try a number over here. I could try a number in here, but I prefer to try a number over here because those would be positive numbers. Let me just pick a number like 5. I don't know. Let me test a number over here like 5. If I plug it into this original problem, so I'm going to go 2 times 5 over 5 plus 3. Is that less than 0? Let's test that out. That would be 10 on top, and the bottom would be 8. Is 10/8 less than 0? No. So that is not true. So this side is the bad side. Now, this is a bad side. What usually happens, unless you have what's called a double 0, which we don't have a double 0. We got a 0, and we got a single asymptote there. We don't have anything double. So what happens is if this is bad, this would be good, and this would be bad. Of course, when in doubt, test it out if you're unsure. Now let's go ahead and try and find our answer. Our answer is right in here in the middle. In here is good. This is the good stuff. But wait a minute. We don't want to actually equal 0. And this one was right here was when it equals 0. So I'm going to put an open dot there. And then, of course, do I actually equal -3? Well, no, you don't ever want to equal that because that's a 0 on bottom, and that's bad. So that's also an open dot. So our answer is going to be just the stuff in here in the middle between those two. Of course, we need to answer this in interval notation. So I am going to write this in interval notation. We start at -3. Of course, we don't want to equal it. And then we go all the way up to x is 0. And again, we don't want to equal that. So there is my answer. That is when that rational function is less than 0. In fact, you know what? We've been graphing some stuff a lot lately, sort of checking our answers or using technology. Let me graph this thing and see what happens. 2x over an x plus 3. Now, I usually like to wrap that in parentheses just to make sure I don't accidentally get that out of the fraction. And then, you know what I should really say is y equals, even though it looks like it graphed it already without that. And check it out. Now, I did y equals. Our whole goal is to know when this is less than 0. When is this thing less than 0? It looks like, well, here's 0. This is above the x-axis. I want to know when it goes down, when it's below the x-axis. And if I zoom out a little bit, looks like the only time it's below is starting right here and going down forever with some kind of asymptote there. Oh, look, that looks like the asymptote might be at -3 on my scale here. So we see that it is from -3 to 0, right in between there. Let's go to the next problem, which is very similar. Let's do this again. Solve, write your answer in interval notation. Here we go. Let's talk about when the top is equal to 0 and when the bottom is equal to 0, because then we can tell when it's greater than or equal to 0. Well, a 0 on top is okay. So when is it a 0 on top? Well, that's when x equals 1. I can just add 1 to both sides. And that's a 0 on top. That's called a 0. Now, what about a 0 on bottom? Remember, that's bad. 0 on bottom is bad. And so that would be, if you add 6 to both sides, that would be there, and that would be, again, the asymptote. So what we do is we do our sign line. Let me separate that earlier problem. We do our sign line here, and we mark the 0, which was 1, and we mark the asymptote, which was at 6. Let me label those. That was the 0, and this is the asymptote. And now we check in the middle, or you know what? Last time I checked on one side because it was easier. In between 1 and 6, that could be pretty easy to check, but I'm going to check over here because I like to check the number 0 when I can. The reason why I didn't check 0 earlier is because we already found 0. 0 was a 0. Here, 0, is that going to be good or bad? Let's try it by plugging it into the original. So let me plug it in and go 0 minus 1 over 0 minus 6. Is that greater than or equal to 0? 0 minus 1 is -1. 0 minus 6 is -6. Is that greater than or equal to 0? Well, -1 over -6 becomes positive 1/6. And that is indeed greater than 0. So this is good. I just found a good side. And then that means this is going to be bad. That's what usually occurs. And then this would be good. It alternates. So it looks like good is going to be from here all the way over. Now the question is, wait a minute, that 0, is that 0 good? Do I want this to equal 0? Yes, it says greater than or equal to, so that's going to be a solid dot. Now over here, that was also good on the right side, so it's going to be that way. But the problem is, what about this spot at 6? That was the asymptote. That was bad. Oh, that's a bad asymptote. And so we put an open dot here because we don't want that to happen. There is our sort of our visualization of this. We just need to write this in interval notation because they said interval notation. So for this side, we're going to go from -infinity, because it keeps going forever, all the way up to this spot 1, and that will be a bracket. So there's the beginning of my official answer. And then, of course, we're going to union that. Remember, CWI uses that big U for union. We could also just write the word or. And then this other side. Now, this one starts at 6, but we don't actually want to equals 6 because, again, that was that bad asymptote. So if I squeeze it in here on the edge, we want to go from 6 all the way out to positive infinity. Okay, and that's the other piece. 6 was not a bracket because we do not want to equal 6. And of course, infinity is never a bracket because we never actually equal infinity. Let's do a little bit more. We're going to graph this polynomial. First thing I want you to do is you should know some stuff about this polynomial. It's a third degree. So usually third degrees kind of look like this. It's not negative in front, so it's not flipped upside down going the other direction like that. That was even hard for me to draw, drawing an upside down one, but a flipped one. But it's going to look something like that. We're expecting it's going to cross the x-axis at 3 times, but watch out. Sometimes you don't always see it because maybe it's imaginary. Let's actually graph this thing on a calculator. We should know some information about it, though. I'm going to use y equals. Go in here, track that. There we go. Hey, looky here. It kind of looked like what I expected. But as I zoom in, I noticed some things, some important things. First off, my Desmos graph is not scaled how I normally like it, so I'm going to fix that in a second. But notice here, this 0 seems to hit and do one of those double zeros where it goes up and then down in the same spot. This is a normal one where it crosses. So it does hit 3 times. It goes up and hits, then it comes down and hits it as it leaves, and then it goes up again, and there's the third one. So it goes, and that was 3. I'm going to change my scale by going to the wrench, and I'm going to go down here and say step size. I'm going to say step size 1, and I also like to turn off the minor grids. There's just too many lines on there. Click the wrench again, and there we go. Now I can see it crosses at -1. Ooh, it crosses at -2, and it crosses at 2. Let me mark those on my graph here at first. It crossed at -1. That was a 0. It went up to it, and then remember it crossed the y-axis at -2, I believe. That makes sense because we should know that there is the y-intercept at the very end. And then where did it cross going back up? I forgot already. It crossed at 2. And it also seems to go that this peak down here, for like the vertex right here, is at 1, -4. So let's graph that as well. So it goes down to 1, -1, 2, 3, 4. Oh, you know what? Their scale is crazy on this. Why did they do that? Okay, so their scale is ridiculous. What was the number again? It looks like it went to -2 and then down to 4. But it looks like we don't even need to go that far. So watch out for this scale. I just noticed that this is -15. So what is that? 1, 2, 3, 4, 5. So what is that? Counting by 3s? 3, 6, 9, 12, 15. So if it counts by 3s, then the 2 would be right here. The 4 would be right here. That's ridiculous. Whatever. So it's going to look something like this, even though their scale is all crazy. It's going to go whoosh. We'll call that good enough for this one. I would use normal graph paper, but I'm kind of stuck using their graph paper. I would just use normal graph paper with a normal scale for this one. All right. Let's try this other one. Now I notice that the scale is all weird. It's the same kind of graph paper. Oh well. Again, I see that's x to the 3rd power, which makes me think it's going to be some kind of like whoosh thing like that. It usually hits 3 times, but we saw last time it had a double 0, a double root, a double x-intercept. Let's graph this one. All right, let's make it so we can see it here and graph y equals x to the 3rd. I'm going to arrow over, plus 3x to the 2nd, minus 25x, plus 21. All right, now these numbers are a little bit crazier, so maybe we do need a different scale. Now, wait a minute, it looks like a parabola. If I zoom out, so this one might need a different scale because this one is like huge. But I'm going to zoom in again to see those x-intercepts. It looks like it crosses at, -7, crosses at +1 and 3. So -7, 1, and 3. Let's mark that on here. -7 would be there. Watch out for the scale. +1, and I think it was +3. Let's find some other important landmarks. First off, again, we actually should know that the y-intercept is going to be positive 21. So maybe that's why the scale is so big. Remember, it counts by threes. 3, 6, 9, 12, 15, 18, and then 21. Boom. Of course, let's go and look at that on our graph. If I scroll and zoom out a little bit, let's zoom out. Yes, it looks like it crosses somewhere at 21-ish. I could zoom in there if I wanted to. Now let me scroll and find that peak up at the top. I'm going to zoom out as well. All right, where's that peak up at the top? Oh, my computer's going crazy. Looks like that peak up at the top is 105.028. Okay, I don't think my graph goes that far. We'll see. Then how about the peak at the bottom? This goes down to almost negative 10. It was at negative 9, a little bit past negative 9. So 2, negative 9-ish. So yeah, this definitely doesn't go up to 100. So this is going to go like up there somewhere and then come down. And then it's going to go down, what was it, 2, almost 2, and then negative 9, so 3, 6, 9-ish, so somewhere right around there. And then it will go back up. So something kind of crazy like that. So there we go. There's the graph of that.